Determine if two sentences are similar. Hi everyone, we're here today with Simon for another exponent mock interview. Okay, Simon, thanks so much for being back here again with us. Can you introduce yourself again for our viewers?
Sure. Hi, everyone. I'm Simon Eisman, and I'm a software engineer at Google. I used to work at Spotify, Etsy, Bloomberg, and Foursquare. And last year, I graduated with an MBA and a master's in computer science from the University of Chicago. And looking forward to this interview.
Okay, awesome. All right, so we have a pretty interesting question to approach today. So let's get started. So the question is, determine if two sentences are similar.
Gotcha. So I guess one question that I have right off the bat is, what does it mean for two sentences to be similar? Are we using, let's say, synonyms or something like that? Or is this like a natural language processing type problem?
Yeah, so I guess you could approach it with NLP if you wanted, but that's maybe too fancy and outside of the scope for today's problem.
Okay.
So you can assume that I'm actually going to give you a list of like words that are considered to be similar to each other. So like synonyms.
Gotcha. Okay. So if you're going to be giving me words that are similar, I guess what we're saying is that if we kind of have two sentences, then what we mean is that like the zeroth words in each sentences have to be similar to each other, and then the first words and then the second words have to be similar, and so on.
Yep, exactly.
Gotcha. Okay. So I guess one of the things that implies is that the sentences have to be the same length to be similar, or rather they have to have the same number of words in order to be similar.
Yeah, that's right.
Gotcha. Okay, yeah, that makes sense. I think, though, one big question I have is still around how we determine the similarity. Like, how do we know if words are similar to each other? You know, are we given a thesaurus or anything like that?
Yeah, so like you're gonna get a list of pairs of words that are considered to be similar to each other. So it is essentially a thesaurus.
Okay, gotcha. I think, all right, that makes sense. Maybe we can do an example. Like, would you be able to show me an example sentence and maybe some possible pairs?
Yeah, good
Let
idea.
me share my screen for this.
Yeah, let's do that. Okay, so there's an example here of like two sentences that are similar to each other.
Mhm.
I really love the code and apples. And then I so like code signal and oranges. And these are considered similar to each other because really is similar to very, which is similar to so. And then like is similar to adore, which is similar to love, and so on. Does that make sense?
Yeah, that makes sense. So yeah, so just to then reiterate, we want each of these words and these sentences to be pairwise similar, one to
Mhm.
one.
Mhm.
And like you mentioned, some of these similar pairs that you're giving to me don't quite represent direct relationships, right? That they could be sort of like transitively correct, if I understand.
Yeah, exactly.
Gotcha. Let me actually rearrange these so we can kind of see that play out a little bit. So we have this together with very and so is another one. And then we have really and very together here. We have love and adore like this. And then we have these pairs right here, which are kind of independent from one another. Okay, so yeah, so this makes sense then. We kind of have like this transitive relationship where in the original sentences, really and so aren't together, like you said, but you know, they're kind of paired together with this very because those are similar to themselves. Okay,
Yeah.
gotcha. All right, this makes sense. One thing that kind of jumps out at me is that this feels like a graph problem.
Okay, how so?
Yeah, so I think, you know, one of the first things we want to do, given like these sort of pair relationships or edges, so to speak,
Mhm.
is that we can build an adjacency list using a hash table where we basically have each individual word as the key and then a list of the directly similar words as the value. So let me actually give an example of what the adjacency list from this would look like. And then we can kind of see like how that would actually be useful in the form of an algorithm. So for example, lead code would map to code signal. Let's start with the simple ones first. Similarly, in an adjacency list, we'd actually want the same relationship back, right? Because what we can notice that for each edge, it's basically bidirectional. So lead code has code signal as one of its neighbor, and then code signal has lead code as its neighbor. It would kind of pop up in that adjacency list together. Similarly for apples and oranges, we have something like this. So these are actually lists on the right-hand side, but for simplicity, I'm not like putting any square brackets around it. Mm-hmm. Now is where we get to the interesting one, where we kind of have a relationship like, let me see. So for example, a door maps to like and love. And the reason we know that is because of the pair that we have here and here. So kind of a door appears twice there for both of them. Yeah. But like only has a door in its part of the adjacency list, and love has only a door within its part. And then lastly, we have the relationship between very, so, and really. So it would be very has really, and so really has very, and so has very. Mm-hmm. Okay, so this is what our adjacency list would basically look like. The reason that we really only care about adding these direct relationships, these like similar pair edges that we've sort of been given, mm-hmm. is that we want to think of this as a graph of connections. We kind of have this relationship between love and adore and like, and that's kind of what gives us an understanding that these are transitively similar. Yeah. And because these are nodes in a graph, we can sort of do an algorithm on them. Mm-hmm. So after we build this adjacency list, one way we can think of the algorithm is we basically go word by word in the original sentence, in pairs, and then we simply perform something like a depth first search, where we're searching from the source word node to the destination word node. And it kind of doesn't matter whether we pick the first sentence's word as the source or the second sentence's word as the source, because everything is sort of bidirectional and mirrored. If we look inside of the structure, we can kind of see that play out. And as a result, after we perform each of the pairwise checks, we perform a DFS on each of those pairwise words. Okay. It's actually also even simpler if the pairwise words are equal to each other, like I and, because we don't need to perform a depth first search in that situation.
Mm-hmm. Okay, yeah, that makes sense. So the depth first search is purely for making sure that you find all pairs of words that are similar, like in a transitive chain, but like not
exactly
each other. Okay, yeah, makes sense.
All right. Is it okay if we implement it?
Yeah, that sounds good.
Okay, awesome. Let me sort of bring up let me comment this out and then bring up like a sample function. Mm-hmm. So we're basically given the two sentences to start, and I suppose the edges. I guess one thing that I would ask is, can I assume that each sentence is given to me as a list of words and that everything is sort of lowercase and free of punctuation, just for simplicity?
Yeah, you can assume that everything's been pre-processed for you already.
Perfect. Okay, great. And then similarly, I'll also have like an array of the similar pairs, which will just be, I guess, tuples or something like that.
Yeah, that works.
Okay, great. So let's give ourselves some space here. All right. So our sentence is similar. And as we said, we're given sentence 1, sentence 2, and the similar pairs, which again is just an array of tuples or something like that.
Mm-hmm.
Okay, so I think the first thing that we do, let's just bring these two sentences together just so we don't forget what this kind of looks like. The first thing we want to do is we want to have a check to make sure that they're the same length. So if the length of sentence 1 does not equal the length of sentence 2, then we can basically just end early, because we automatically know that it's false because they have to be pairwise similar to one another for each word. So that's one part of the algorithm. Now what we basically want to do is we want to build the adjacency list. So let's create a graph. We'll use a default dict here just for simplicity. Now for pair in similar pairs. Let's break this out a little bit so it's a little easier to read. So now what we want to do is we want to do like this mirrored addition inside of our adjacency list. So graph of word 1 dot append word 2. And the reason we can do this without any checks of if it exists is because of the default dict.
Mm-hmm.
Okay, great. So maybe I would check if this graph looks like how I'd expect, but we could always test this later with unit tests to make sure that we've kind of built it correctly. And now what we want to do is we basically want to iterate over each of the words pairwise in the sentences and then perform the depth first search. So let's get an index. And we can similarly get each word in the sentences. And now we perform a depth first search. So we'll want to create a second function that does the DFS, but let's assume for now that it exists. So if DFS on the source and the destination, actually, if not, right, if we do not find it, right, because that's effectively what we're looking for. If we don't find it, then we return false. And then at the very end of the algorithm, if at no point did we not find it, that means that all the words were found. All the pairwise connections exist, and therefore the sentence as a whole is similar. So this will sort of serve as an early end stop. So now let's actually give ourselves a DFS function here. So DFS, we want the source and the target. So let's say current word, which could be the source or wherever we start. Actually, we actually have to pass all this information in. So this isn't enough parameters. So we actually need to pass in the graph. And we also need to pass in, as part of a DFS, we need something like a scene set to make sure that we don't accidentally have like this infinite loop where we keep searching back and forth, but we keep seeing the same words. That will kind of make our algorithm run forever. So we actually need an empty set here to start. And as part of this code, we then need to know what the overall adjacency list looks like and whether we've seen, what words we've seen as part of our current DFS search. So if the target word equals the current word, basically did our depth first search pan out, then we simply return true, right? We found a similar connection within our adjacency list. Mm-hmm. what other base case do we need to include here? Whether it's in scene, so that's another one. So if the current word in scene, that means that we've seen it before as part of our traversal. We can simply return false because this path in the DFS has not panned out. And I think that's all the base cases that we need to take care of. If it's found, if a path doesn't succeed, yeah, I think that should be fine. So the actual core of the algorithm is iterating over all of our neighbors inside of the adjacency list. So, at each point we want to, start with the source. Let's say really, we iterate over its neighbors, such as very. When we get to very, we iterate over its neighbors, which is really and so, and then, that will kind of give us what we want. So for neighbor in graph of current word, right? That will give us the neighbors via the adjacency list.
Mm-hmm.
When we have that, we want to continue. We want to recurse and do another depth first search. So let's pass in all the same information we have, except now we have the neighbor as our current word and the target word. That didn't change. So actually something I forgot to do, which is critically important, is we need to add the current word, because otherwise this will recurse forever. So it's something we have to make sure to do.
Right.
So if it's found, we simply return true, right? That's good enough for us.
Yep.
If for any of those words it didn't return true, that means we can simply return false. It means that this DFS failed. So let me take a look at this just to do a confidence check here. So we have seen, that's correct. We iterate over these words pairwise. Ooh, something I missed, big thing I missed. If the words are the same, yeah, if the words are the same, we want to make sure that we aren't performing a depth first search. So if word one equals word two, right? Then we simply continue. Yeah, I think that that's a reasonable step. So I guess one assumption I made as part of this is that the same words are already similar to each other, and therefore would not appear inside of this similar pairs list that we're given. So this is actually necessary. We might otherwise run into a situation where it crashes potentially, or incorrectly gives us the answer. Yeah. So this is an important check. Mm-hmm. But yeah, this I think looks pretty good. Should we run this against some unit tests?
Yeah, I'd love to see your testing code.
Okay, perfect. Let's kind of think through. Let's think through what we would want that to look like. So we definitely would want to take care of, say, basic cases like, let's kind of take this right here. That could be a good starting point for us. But we definitely want to take care of some basic cases like, what happens when the sentences are empty, right? Or what happens when they're different lengths. That would be part of my unit test suite, but let's actually check it maybe against some of the meatier cases that actually test the core functionality. So whether they're fully similar or partially similar. So let's see. So we might have a test like, sentence one equals, I will lowercase these. As you said, there's some pre-processing here. So I really love leap code and apples, free from punctuation as well. And similarly, code signal. One thing I think that we've ignored as part of this is like plural and singular versions of these, but I think that that's okay for our purposes, if that's okay.
Yeah, that makes sense.
Okay. If we had a full NLP problem, that would probably need to have been taken care of, but
yeah.
Okay. And what are the edges here? So this like long list of edges that we had over here. We need to map these basically. So similar pairs. Okay, I think this should encapsulate all of them. And just so we don't have any bias here, let's actually just rearrange the order of these so that they don't appear in a preferential order. And now what we should expect here is something like, we can print this. Our sentence is similar. We provide sentence 1, sentence 2, and then the similar pairs. We'd probably want another unit test here where they're almost the same, but they're not. So let's run this unit test first, just to make sure that we have a true here.
Sure.
Okay, great. That doesn't tell us anything because we also need the converse case.
Yeah.
So let's try another one where they're basically the same, except I'm going to say definitely. And actually, this will be an interesting case because definitely doesn't appear inside of our pairs at all.
Yeah.
And I wonder if our code will catch that. I think it will because we're using a default dict, so it just won't iterate over any neighbors, I believe. So I think that should be fine. So what I should expect here is a true and then a false. Great. Okay. Just to make sure this works, I'd run it against those other test cases that we looked at, but like the empty and the not the same size. But I'm pretty happy with this.
Perfect. Okay, so can you tell me what the runtime complexity of this would be?
Yeah, great question. So in the worst case, let's think about this. In the worst case, we're basically performing a full DFS n times, where n is the number of words in each sentence, assuming that they're the same length. And one thing that we do know also is that, so at the very least, it's, O of n, but it's actually n times the time complexity of a DFS. The time complexity of a DFS is O of v plus e, I believe, where v is the number of vertices and e is the number of edges in the graph. So I guess technically it's n times v plus e. I think we could actually probably simplify that because there is likely some relationship between n and v and e, or at least, put simply, there is likely some relationship between the number of words and the vertices and the number of pairs that were given to us and the vertices and edges. But I think that this complexity probably gives us a good enough lens on the problem.
Okay, yeah, I'm happy with that. Okay, so one last follow-up question for you. So with Python interpreters, there's usually a recursion depth limit of 1,000. So what happens if you have a graph where you have a chain of similar words that's longer than 1,000?
Yeah, it's a great question. So it might basically lead to like a memory issue of some kind if we're kind of going too deep in the recursion. So we'd probably want to reduce that memory footprint. You can also perform a depth first search iteratively, not just using recursion. So I think that would be an approach we could use to limit any issues that might arise from that. So, and it'll reduce the space complexity of the problem. So that inherently kind of solves these memory issues.
Right, exactly, by using a stack, right, instead of using recursive function calls.
Right, exactly. Yeah, you can keep track of that within your function's local memory.
Yeah, exactly. Okay, all right. So congratulations on finishing the interview. You did a fantastic job. I think this is a good place for us to pause and analyze how this interview went a little bit. So, what do you think went well, and what do you think you would actually want to do differently next time?
Yeah, I think that at the outset of the problem, there were some good clarifying questions asked. I think that at the core, this problem is quite general, right? Or it's at least
Mhm.
ambiguous in a sense that there's a lot of questions you kind of need to ask to really understand the core of the problem, right? Like we're not, as part of this, we're not really doing an NLP type problem. We're doing some problem solving in like a more basic sense. So I think I asked some good clarifying questions to get to that point, because otherwise it
Mhm.
kind of felt like a very ambiguous problem.
Right.
Another thing I think is that the code was relatively clean. Clean, I felt like I had like a direct path to the solution, but there
Mhm.
were some issues where I kind of didn't realize an edge case, but I eventually caught it later on. And um, thankfully, I didn't have to do very much finicking with the code because the unit test passed.
Mhm. Okay, yeah, that makes a lot of sense to me, and I definitely agree with a lot of those points. And I also really like that you had the really crucial insight of the problem where you recognize that like word similarity as it's given to you in pairs is not it's not the extent of it, right? That you can have like
Yeah,
transitive word similarity. So that was really smart, and I like that you were able to recognize that this problem has a graph structure by recognizing that like
yeah,
you have pairs of entities with relationships between them, right? And that's
yeah,
usually like a signature for like either it's going to be a graph or a tree or possibly a linked list problem. Yeah, and then like you seemed like you had a really like deep familiarity with how to implement DFS, and that's really important for doing well in interviews because most graph problems are probably going to be some variant of some graph traversal. So that's like
yeah,
one algorithm that's great to like have in your toolbox. Yeah, and like one other small things that I really like your use of default dict that made your code a lot cleaner, and it also handled the cases where like you have a word in the sentence that wasn't given to you in the
right.
thesaurus. That
Yeah,
handled
I
it really
love default
nicely.
dict.
Yeah,
Yeah, it's a great
yeah.
structure.
And then, so like one just like minor thing that I think we sort of talked about actually is that like one clarifying question that's also good to ask is to ask about like the scale of your input. So in this case, your
Yeah,
similar words chain could have been longer than 1,000, right? Which would have been a problem for doing recursion in Python.
yeah, that's absolutely true.
Mhm. Yeah. Okay. So thank you so much for being here with us today. I think we learned a lot from watching you do this interview. And thanks so much to our viewers for joining us today. Good luck on your upcoming interviews. And thanks for watching, everyone. Bye.